All right, let's get into it. So demystifying polarimetry. First, we're going to talk a lot about the food chemistry experiments. I think especially right now, we have a ton of educators that are really interested in food chemistry and forensic chemistry. I think everyone's just a little bit burnt out and they're looking for new applications to get their students excited and interested in chemistry again. So we're going to focus on the polarimeter experiments that are in that book. We're going to talk a little bit about polarimetry and why it is used in food chemistry. In fact, it's used like in food industry really commonly. So a lot of the experiments we're going to talk about are actually done in industry and in the field. So it's a great way to get your students looking at what would actually happen if they got a job as a chemical technician or when they actually go out into the real world. So we're going to do live data collection with our polarimeters today. And if you want to follow along and have the data appear on your screen at the exact same time, you can download, make sure you have graphical analysis, the free version, download it onto a device. And if you haven't already, do that. Go to our website, get the free version, and then you'll be all set by the time we get to that part of the talk. Okay, so the food chemistry, we have a book called Food Chemistry Experiments. They don't all involve the polarimeter, don't worry. They also involve temperature probes, pH probes. So odds are you have something that you can do, something from our food chemistry experiments book. In fact, Noose was one of the main authors on it. Noose is a big proponent of the food chem and the forensic chem. So he has all the answers if you have any questions about the book.
Thanks, Melissa.
And so one thing I do want to plug here is our books are amazing because it's only about $50 and you get a book that's a site license. So all of your faculty, all of your teachers can use that book and those experiments. You get free access to the electronic resources, which includes Word files for all the experiments. So you can edit them, photocopy them, distribute them as much as you want. So I highly recommend getting books, especially, you know, a lot of people are going back into the classroom right now. They're refinding all their Vernier stuff and be like, oh, what do I do with this? Our books are a great way to get you started with that. So food chem experiments are a good way to get you started. So today we're talking about two experiments. We're identifying sugar and sweeteners in beverages, and then we're going to look at a kinetics experiment for measuring sugar inversion. So let's talk about, Vernier has two different kinds of polarimeters. So the first is this Go Direct Polarimeter, and this works via Bluetooth or USB. It's also a little bit newer of a model. And then we have an older version of the polarimeter, which has cables and works with an interface. So first off, what is polarimetry? So it's just another type of spectroscopy. It looks at the different ways, you know, molecules interact with light, and it exploits the fact that light is polarized. A very common experiment we do with students to teach them about polarized light is sunglasses, right? You take sunglasses that, polarized sunglasses, and you hold one straight, and that only allows plain polarized light to go through sunglasses. So if you fix one sunglass lens, and then you get another sunglass lens, kind of as illustrated in these pictures here, and rotate that one while light's coming through it, you'll get a really bright view through, and then it will slowly dim and get really, really dark. And that's actually expressed with a cosine squared waveform like this. So this is when it gets really, really dark, and then it gets really, really bright. And so what chemists have done is they've exploited this, and any chemical that's in an enantiomer that you know, has an R, an S, or a plus or a minus in front of it, you can put that in between the fixed polarizer and then the rotating polarizer, which is called the analyzer, and that chemical will rotate that plane polarized light So this peak that without any chemical in there will be at 0, or any non-optically active sample will be at 0, will be rotated or shifted in a different direction if there's an optically active sample in here. And so this is a very quantitative, very well-known phenomenon. In fact, it's described by Bayet's law, which if you look closely at that, looks a lot like Beer's law. You have a specific rotation value that is inherent to the molecule. So just like an extinction coefficient in Beer's law with visible absorbance spectroscopy, you have a specific rotation value that's known to a molecule. You're dependent on the path length, you're dependent on the concentration of the sample, and then you get an observed optical rotation from that. What else can I say about it here? So today, we are gonna be using the Go Direct Polarimeter to collect data. And I'm actually gonna do it with a Labquest 2 today. Labquest 3 is our new version of the Labquest, but I know a lot of people out there have Labquest 2s. So I'm gonna do a shout out to Labquest 2s today. And we're gonna take data with the Go Direct Polarimeter and our Labquest 2. If you have kind of one of the older chemical polarimeters, definitely let us know if you have any questions about it. And we'll talk briefly about the differences later on, but we'll do some Go Direct today. And then I'm going to, since the polarimeter is a little bit more of an expensive instrument, most people can't have one for every student, one for every student group. A great feature of having one of the more expensive instruments and being able to collect data with the Labquest is to share data out to graphical analysis, and then to even share data out online through Graphical Analysis Pro. So that's why I wanted you all to download the free graphical analysis. So make sure you've done that. And let's get started. All right, so I'm going to pull up a piece of software here called Labquest Viewer, so you all can see my Labquest Viewer screen, my Labquest screen, excuse me, since it's kind of tiny in the little video corner. I'm going to connect my Go Direct Polarimeter to my Labquest. So first I got to turn it on. It's Bluetooth broadcasting. Going to click on Sensors, Go Direct. And for some reason, this always, I have to select it before it actually will show up. So now we're connected, and you get that big red box that says you're connected. And so now, before I even get started, say, you know, I'm the student who's setting up the polarimeter at the Labquest hub, but then my whole group has their phones out or their Chromebooks out. They want to connect to that Labquest to make sure they're getting the data. So I'm going to open up my graphical analysis, and we're going to go ahead and give you Graphical Analysis Pro. There's a code here. Oh, I'm hiding it. There's a code here. Wow. And this code will give you Graphical Analysis Pro free for 2 weeks. So hopefully Noose or Angie is going to put that into the chat so we can copy and paste. I'm going to manually type it in here. IE capital M 2 N capital A M 6 capital C. All right. Yep. Thank you. Someone put it in there, Angie. All right. So I just type it in here where it says activate additional features. Click submit. And now I have Graphical Analysis Pro. So now I want to connect to my Labquest. So I'm going to click on data sharing, and this is just the teacher. This is just the group that's in the actual classroom with it. Let's see here. Let's do some troubleshooting. It's not seeing P's. Let me restart my graphical analysis. Data share again. Local P's, there it is. All right, so now I'm connected to my Labquest here as the teacher or my group of students that are all in the same room as the Labquest. But I also have Luis, who's at his football game this weekend, and he wants to join live. I have all of you out there that want to collect data live with me. So your screen looks like this. You've already joined GA Pro, but you're still on this welcome screen, right? Okay, so you go ahead, and this is actually just my cell phone, so I'm going to connect to it, but you all can connect as well. So I want to data share my session. So me as the teacher, I'm going to click on the little TIE fighter and start my session. But then you as the students will click on data sharing. And then in the online data sharing, you're going to type in this code, RPR5D. And then I'm pretty sure that's an N. Oh, nope, it's an M. Always got to go to this side. And connect. And so now I'm connected to this data sharing session as well. So locally and via distance, we're all connected to the data coming from my Labquest. Did everyone get that? Is everyone connected? Everyone wants to follow along, do all the data collection and analysis with me? All right.
Connected.
Yeah, is it working for you, News?
It's working for me.
Great.
Hopefully it's working for other folks.
Yeah, great. Okay, let's get some data going. All right, so I'm in Vernier land, and when I connect a sensor, I just press collect and see what happens. So it's telling me what it needs me to do. It needs me to calibrate with water. So I have my tube with water, and I'm going to put it in there, and I'm going to calibrate now. And so it takes a little bit for calibration to happen. So the polarimeter, the fixed polarizers in the base here with the light source, it's going through this sample cell. The sample cell has a ruler on it, which you probably can't see very well, but that's what determines the path length. Most polarimetry is done at 1 decimeter or 10 centimeters. So all my solutions here are to a 10 centimeter height. But if you vary that amount, then you just vary it in Bayes' law. And then at the top up here is where the analyzer is. And this is where the polarizing filter is rotating. The Go Direct version has a motor in it that's running for you. The older version has this manual analyzer. So students actually have to manually move it with their fingers. But now my calibration is done. So I'm going to say, okay. And I'm all about a warm fuzzy. Anytime I'm doing any kind of calibration, data collection, if I have just calibrated my pH probe, I put it back in the pH 4 buffer to make sure it still reads pH 4. If I'm doing absorbance data, I check after calibration to make sure I have a flat line. So now I've done polarimeter data, and I want to make sure that my peak is at 0 because that's water. It should not be optically active. It should be giving me a 0 value. So this is the cosine squared waveform that we talked about earlier for water after calibration. I want to make sure it is the angle at maximum illumination is at 0. So there's a couple ways I can do this. One, I can highlight the peak and click on statistics. And sure enough, it'll tell me where my max value is. So it tells me your max illumination at whatever angle. And this says it's at 0.12. That's kind of close to 0, but it's really not as close as I want it to be for actual quantitative data. As you can see, there's a lot of data being collected. So noise really contributes to statistics because it's just picking your max value. So this isn't going to give you the most accurate data, but it gives you a good feel for it. So you can always use statistics, but for the most accurate data, you actually want to use the fit that mathematically fits this data, which is the cosine squared wave. So to do that, I go to apply curve fit. And from the list of curve fits, I pick cosine squared. And I hit apply. And now I have my cosine squared fit showing up. And if you have students that are calculus based, spend all the time you want talking to them about what this waveform is, what all the parameters mean, the shifts, all that. But if you don't, and I never had chemistry students that were calculus based, just tell them it's the opposite of C. You'll get through the rest of it in calculus. And the opposite of the C value here is 0.003. So that's really, really close to 0. That's much more quantitative than that point when we were getting. So yay, I have my warm fuzzy. I have an angle of 0 at maximum illumination after calibration, which is what it's supposed to be. So how's everyone doing with that? You all have the data on your own computers. You're able to analyze it yourselves. Any questions about any of that? Noose, how's everyone doing?
One question about an invalid code. I'm working on that with the participant right now.
Oh, okay.
I
Great.
mean, I got the data, so I think it's, folks. I'm close to Melissa, but I'm about a mile away at my house, and so let me check RPR 5SM.
It's
DM. I'm sorry. I typed that in wrong, so I apologize. RPR 5DM.
All right.
Yeah, you'll get the data immediately once you get the right code in there.
Awesome. Okay, so now we've done water. So the whole point of this experiment that we're going to look at today is looking at known sugars, sucrose and fructose, and then comparing those to commercial beverages and having the students identify what the main sugar is in the commercial beverages. So I have a 30% sucrose solution here that I'm going to run. And when I press collect, the data is automatically stored. It's just hidden. And now it's going to run my sample of sucrose. And right away, I see my predominant peak is shifted positively away from 0. So I know right away sucrose is a positive enantiomer. It's shifting light positively. So that in and of itself is very illustrative for students. You know, I always relate to students that have such a difficult time understanding stereochemistry. I had a really hard time with it as a student. The difference between right-handed and left-handed molecules and actually visualizing that and what it means when you get to it in AP Chem or an organic chem and how chemical reactions vary with that. This is just a great way, another tool we as chemists have to show our students the differences. Just that first off the hand look, but now I need to make it quantitative, right? So I'm going to go in here and I'm going to do my cosine squared waveform again. And the opposite of C, 20, okay. This isn't as easy as water, that should be 0 to do that math in our head. We actually need to do a little bit of math. This Bayes' law that I mentioned earlier, alpha is what we're getting right now is the observed optical rotation. That's what's coming off of the data. Again, the specific rotation is a known, it's something you get from literature. It's specific to a molecule. Sugar solutions in particular are very well researched, and they have literature values that are very well known, just like extinction coefficients. We look at a lot of sugar samples with polarimeters. But we need to also account for the concentration and the path length. I went ahead and made the path length 1 decimeter, so I can make that math easy for myself. But the concentration is not 100%. It is not a 1 gram per milliliter solution. Yeah. And so because I need to do a little bit of math, I have made for you a nice calculator sheet here. That's also, oops, I forgot to delete these from when I was doing my runs earlier. So I have this nice little calculator sheet in that Google folder with all those free resources. And this will help you do some of that math a little bit more quickly, especially when you're preparing solutions for students. This is always something that I like to have a little cheat sheet in the background. But my 30% sucrose solution, if I go here, this gave me a observed optical rotation of 20.08. So I go over here and type in 20.08, and these are all my trials that I've done with this solution. And then how this sheet works is the observed optical rotation down here is the average of all my 3 trials. And then I have 1 decimeter, so you can change that if you didn't quite fill it to 10 centimeters, if you filled it a little bit over. The concentration of the solution, and that will then calculate your specific rotation. So the specific rotation of sucrose is known to be about positive 66, and I'm getting 66.5, so I'm very happy with that.
Oh, that's good data.
Yeah, that's really good data. And so now we're going to do the next known sugar, which is fructose, and fructose is a negative rotator. So I would expect when I collect data that it shifts from the 0 that we saw in the beginning, or that the calibration is set to the left, to the negative side. And in fact, it does. Yay. Physics works again. And once the data is collected there, I do the same thing, apply curve fit, cosine squared, and then the opposite of the C value, negative 27.41. So I put that over here in my sheet. And I'm getting minus 91.29, and its known value is minus 92. So I'm very happy with that. And now to get to the unknowns, to get to some soft drinks. So I'm going to start out with Mountain Dew. And Mountain Dew is, I think, pretty well known for being one of the higher sugar content sodas out there. So let's see if that's true based on my samples, and let's see if we can determine what the predominant sugar sample in it is. And to me, that looks like it shifted it a little bit negative. It's going to the left there. And so I'm going to guess that it's fructose. And then if I can confirm that by looking at the label. And I think, you know, if you wanted to kind of conceal it from students, like, oh, here's a couple of different samples, pick the one that's the soda that has high fructose corn syrup in it. You could also frame it that way. But it is indeed shifted left. It has a peak there at 6 degrees. So its observed optical rotation is minus 6. Oh, I forgot my last couple digits. Minus 6.08. Oh. There we go. And so I can guess that it's fructose. I can use my specific rotation that I calculated here to calculate a concentration. So assuming the only sugar in Mountain Dew is fructose, it would have this concentration of fructose. It does get a little bit messy because there's more than one type of sugar, and there's more than one type of optically active sample in the Mountain Dew. But it gives students a really good feel for what's in the solution and how I can compare that to the label. So my next sample is Rockstar energy drink. I also picked Rockstar energy and energy drinks in general because they are also high in sugar content, but they tend to be higher in sugar content of glucose or sucrose. So they rotate light positively and follow more of a sucrose model. And indeed, I'm getting a little bit of a positive shift here. So I can go through and get the actual value, the observed optical rotation there of 3.8. And then I have for my Rockstar energy drink. And then I can do the same thing with Monster energy drink. And
I don't want to drink any energy drinks anymore.
Well, I was about to say, this actually gives a really good, you can have a really good conversation too about nutrition and what's like kind of commonly perceived as better nutrition, nutritious sugars, since the Rockstar energy drink has more glucose and sucrose. And then there's kind of this negative perception of fructose, which is in the Mountain Dew. And it just leads into a lot of conversation you can have about not only food chemistry, but nutritional chemistry, and comparing what is determined, with an instrument versus what's on the label. And actually just talking about polarimetry, like Coca-Cola has 1 million polarimeters in their facilities for quality control and testing like that. They obviously don't look exactly like ours, but it's a very common technique used in the food industry. And it just gives your students kind of an idea of what that whole industry looks like. All right, so the Monster energy drink, 5.718. Okay, and again, we look at those, so Mountain Dew, if you said all that was from fructose, has almost as much fructose in it as Monster energy drink has sucrose in it. You can do this for a bunch of other samples. If I had found, I always like to do the sugar-free ones, if they're actually sugar-free or if they're aspartame, you'll see the difference. So if you get a diet soda that has aspartame in it, you'll see the shift from aspartame. The natural sugars that are marketed as natural, they usually have glucose in them. So you can get fun with this, and you can have students run a bunch of known standards. But there's a lot you can do with it, and that is some fun samples there that you can investigate. Yeah, what else should I say about that, Noose? Do you have any other comments or questions? Yeah, any other comments or questions about the soft drink investigation?
I think what strikes me the most here is the fact that you can take that one sensor and share it, so that here's a physical property that we might have, when we were speaking of, particularly organic chemistry, we might have waved our hands at, but there was no way to demonstrate it. There was no way to, you could use a hand polarimeter, but there wasn't any other real easy way. That you just collected what, 1, 2, 3, 4, 5 sets of data, 6 sets of data in 10 minutes and shared it with the world. I think that's kind of neat. I would love to be able to do this in my classroom now.
All right, yeah, and if you have any questions, definitely throw them in the chat. Yeah, I think what I really like about our polarimeter in particular is that it's just so accessible for students to really have another way to talk about enantiomers. And sugar solutions in general are really cheap. They're no waste disposal. You can have students play with them all day long, and it's really very low cost. It's just a little bit sticky. All right, so if no one has any other questions about the soda experiment, we're gonna move on. And I'm gonna show the next experiment I want to talk about is this measuring sugar inversion. And you can actually use the polarimeter to investigate kinetics experiments and chemical reactions. So it's very common in biology and in biological samples that enantiomers will bind only, you know, if you have an R and an S of a certain compound, an enzyme will only bind the R or only bind the S. And that is by design, right? Enzymes are very, very specific for very specific molecules. So you can kind of talk about some of that in a biochemistry perspective. And in food chemistry, biology is very, very important. So we look at this reaction that involves a sucrose, a disaccharide, and an enzyme that is very easily commercially accessible. Flynn sells it. Lots of different chemical companies will sell invertase. And that will bind sucrose and break it into glucose and fructose. And so you go from an optical rotation of sucrose that's plus 66 to less than that, because the fructose is minus 92. So you'll see a decrease in that observed optical rotation from the polarimeter. You can also catalyze this reaction with acid. So it's really nice in a chemistry environment to have an acid catalyzed reaction and just talk about really simple kinetics. But then to build on that with a biological sample with an enzyme gives a lot of great comparison. So I'm not going to actually do the experiment for you here, because as you can see by my x-axis there, it takes about an hour to measure the full reaction with the enzyme. The acid catalyzed reaction is a lot faster. But what I do want to show you is the Go Direct Polarimeter connecting to instrumental analysis, which is our free software for it. So in case you don't have a Labquest and you want to just take data directly with the Go Direct Polarimeter and a computer or Chromebook, we're gonna I'm going to show you that with instrumental analysis. So make sure you go ahead and save your graphical analysis. That's all we're going to do with that. You may want to rename the data files. To do that, you go into the data table and click on the little ... next to the dataset options, and then you can rename. So remember, we started with water, then we went to 30% sucrose, 30% fructose, Mountain Dew, Rockstar, and then Monster Energy drink.
So they're in the same order as on the spreadsheet. Is that right, Melissa?
Yes, they are. So if you want to go through and rename all those and save that data, then you'll have that data. But I'm going to go ahead and close. I'm not going to save. And now I'm going to open instrumental analysis. And this is a free piece of software. We designed this very specifically for some of the chemistry instruments that needed a lot more specific setup that graphical analysis, really, we didn't want to wedge it into graphical analysis. That includes the gas chromatograph, our Vernier Mini GC. Anytime you're doing voltammetry, which right now is with our Go Direct cyclic voltammetry system, or our Go Direct Polarimeter. So my polarimeter should be broadcasting the Bluetooth signal. I had to disconnect it from the Labquest, and sure enough, there it is. So I'm going to connect to my polarimeter. Say done. I could also connect via USB if I wanted. And I have to do that calibration again. So I'm going to do my calibration with water. And it'll take a little bit. And I will have to say, I really love the Go Direct Polarimeter over the older style manual polarimeter we offer for kinetics for a very, very important reason. The Go Direct Polarimeter will do kinetics automatically. Like, it has that motor in it, it knows what time, and it has a timestamp associated with it. To do a kinetics experiment with the older polarimeter that just has the student moving the analyzer, you actually have to have the student record this time 1 minute, after start, and then you do the whole manual rotation. You get that cosine squared waveform, and then you have them calculate the observed rotation, and then they plot it manually themselves. which is fine, which is a great way. It's a good skill for students to learn. But if you happen to have the Go Direct Polarimeter, you can not only do the optical rotation mode, which is what we were just doing, that has the cosine squared waveform, but you have this mode called kinetics, which actually makes the observed optical rotation on the y-axis and time on the x-axis. So I can set up a sample rate and a duration. So if I have a long enzymatic reaction, maybe I just want to take data once every 30 seconds for an hour. Or if I have a really quick acid catalyzed reaction, I can do once every second for 10 minutes or something. So that's pretty nice. So I can go ahead and press collect. Again, I'm not doing the whole reaction for you here, but you can see that as I switch samples, my optical rotation is being displayed versus time. So I put in my 30% sucrose solution, and I am getting an optical rotation there of 20 degrees, which is what we found earlier when we did the cosine square waveform and fit. So any questions about any of that? How's everyone doing? All right, well, I'll stop that. I'll minimize that. And so again, the sample data for the enzyme reaction is in that folder if you wanted to see it, since I didn't collect it for you today. And those are the two experiments that the food chemistry book has. Pretty simple, pretty straightforward. You can do those at kind of any level, really, depending on what you're trying to teach your students. But we also feature the polarimeter really heavily in our organic chemistry with Vernier book. Because polarimetry is used a lot in organic chemistry, it's very heavily used in the pharmaceutical industry, because you definitely have to know the difference between R and S and when you make one versus the other. Again, because of that biology component, pharmaceuticals are going into your body, so you need to be know what the R does and know what S does. So there's a lot of experiments in there about it, but we also have some free experiments online. Understanding polarimetry goes through basically learning by its law and talking about how concentration affects your observed optical rotation, how path length affects your observed optical rotation. And then we have some kinetics reactions, and then we isolate proteins and sugar from milk, so you can see how good your isolation was. And then looking at different enantiomers. So those are all free on the website. Just go to either the polarimeter, go to the polarimeter page for which one you have or which one you're interested in, and you'll see those free experiments there. All right, and as we shift kind of away from polarimetry, I just want to make sure everyone's aware that there's a ton of great resources on Vernier.com. So you guys signed up for this webinar today. We've been doing these kind of since the beginning of pandemic. So there's a lot of free past webinars on our website. If you need something to help with titration, say you don't know how to set up a titration with our equipment, or you're looking for some ideas for AP Chem, or you want to look at our spectrometers. We have lots of webinars for all that kind of go through an experiment just like I did today. And we use the appropriate software, Logger Pro. I mentioned it briefly because you use Logger Pro with this original polarimeter. It is not a free piece of software, but it is a site license. You purchase it once and you have access to it for a very, very long time. So a lot of people don't even know that their school or their department has a Logger Pro site license. So definitely call us up, ask us, and we can find that information out for you. Graphical analysis is free. It uses basically all of our sensors, pH, temp, gas pressure. We talked a little bit, well, we gave you a trial version code for Pro, and I'll talk a little bit more about the differences here in a minute. Spectral analysis is if you have a spectrometer, that's SpectraVis Plus. Any of our UV vis, our fluorescence UV vis, our emission spectrometers all work with spectral analysis. And then the instrumental analysis we showed for polarimetry, mini GC, and cyclic voltammetry.
Hey, Melissa, can I ask a question?
Yeah.
There was a question posted about the reaction kinetics experiment in the organic book compared to experiment number 14 in the food book. And I honestly didn't know the exact answer to that. How similar are those two experiments?
So the one in the food chem book has the enzyme reaction in it.
Okay.
The one in the organic chem book does not have an enzyme reaction in it. It just has the acid catalyzed reaction. And it looks at it just from a little bit more of an organic slant. And then the one in the food chem book really focuses more on the invertase enzyme.
Okay.
Oh, that's a good question. Is there a reason why you'd get the Go Direct versus the original chemical polarimeter? So people feel very strongly about this, I've learned, since the two have been out. Because of all our Go Direct sensors, I feel like the polarimeter is one that's a lot different from the original. Some people really want students to do it manually. They want students to rotate that analyzer, get the cosine squared waveform, do all the data analysis and collection for kinetics and static samples. Some people really just want maybe a number to be spit out of them. And while the Go Direct polarimeter, you can still do that manual data collection like we did today, you can just have it sitting on this optical rotation channel. And I can, like right now, it's got a sucrose sample in it, so I can just write that down. When I switch it out, I put in my fructose sample, and now I get my optical rotation without having to do the waveform, without having to do the calculation. So some people really like that. And some people really want to use it for kinetics and just want to be able to put it in and do kinetics reactions. So it really depends on your motivation behind why you want a polarimeter in your classroom in the first place. If you demo video using the chemical polarimeter. I don't think so, but we can do it right now because we got plenty of time. So let's close that out. I got my Labquest here. So you'll see that the chemical polarimeter is really, really similar in how you take data in comparison to the Go Direct. You just are manually rotating it. So I got the chemical polarimeter here, and I need to plug it into my Labquest. So again, this one has cables attached to it. So you have two cables. One goes into the digital port at the top of the Labquest. Oh, let me switch to
I was just about to say, hey, we don't.
Sorry, I thought it was still on here. So it has two cables. So you either need a Labquest to take data with it or a Labquest Mini. It will not work with a GoLink, for example. I also don't recommend it with a Lab Pro. So one of the cables goes into the top port. So the Labquest has two ports in the top and 3 ports on the side. The top 2 are digital ports. Chemists don't use these a lot unless we have drop counters or a chemical polarimeter. So that goes in the top here, and then the analog ones are the one you're used to. This is where your pH, your temp all plug in. So I'm going to plug in my digital and then my analog. And you'll see that in my Labquest I'm showing here, you see your channel for illumination and your channel for angle. And unlike the Go Direct version, I have to do my own calibration. So I put in my water sample, I press collect, and I manually rotate the analyzer at the top here. And you can see this looks a little bit different because the manual one it does not know anything. You have to tell it everything to do. Sorry, I don't know if you saw me rotating it, but you just rotate like this as the cosine squared waveform comes in. So now I have to determine water for myself. So I can do everything we talked about both previously. I can do statistics and I can do cosine squared. So I'm going to go ahead and do cosine squared, perfect, illumination, cosine squared. And it's still the opposite of this C value. So water came out, the angle of maximum illumination came out at 100. So now every sample I put in, I'm comparing to 100. So you just have to do that one additional subtraction. Alternatively, I could zero out the sensor. So a lot of people don't know about this, but I can manually go through and I'm looking at that illumination value and I want to find its maximum or its minimum. You could do either one. I prefer maximum, but however you want to set it up. We'll do the minimum since I'm around here. But you can see why this isn't super accurate and you're still going to have to do a subtraction off of water. So maybe something like that. And then I zero. So all I did was click on the blue box here and press 0. And so now that zeroes out. And so then I can repeat it with my water, which is what I would have to do now since I lost that. And so again, I have to manually rotate this. So nothing happens until I manually rotate it. And so your peak will go through, do a curve fit for water, cosine squared. And see, it's still not quite on 90, but anyways, so that's the main difference is you have to find your water peak first. And so I'm going to store that as my water. And then I'm going to put my sucrose in. Press collect. And then I gotta, again, nothing happens until I manually rotate this. And then it's not quite as aha moment-y because now I have to pull up my water sample. But I can do that up here, all runs. So that's my water. And now my sucrose is clearly shifted right. Do the cosine squared, do the subtraction, and then I get my observed optical rotation from it. So that is the demo of the chemical polarimeter.
I did find a couple of videos on the website of a much younger Melissa. Oh boy, doing it with Logger Pro. So there is, the older ChemPol can be used on computers with a Labquest interface and Logger Pro. I want to verify with you before I say this out loud, but I'm going to go ahead and say it out loud anyway, Melissa, because you know me. Will the ChemPol work with instrumental analysis?
It does not. It does not work with instrumental analysis.
Okay,
Yeah.
well, that's good to know. Okay.
Yeah, so if you want to use a polarimeter on a computer, you need an interface and Logger Pro software.
Okay, I wanted to verify that before I said it out loud, but I said it out loud anyway. Does any of the other software replace Logger Pro if a student cannot run Logger Pro? The question came up in the chat, and I'll throw it out there too. It says, does any of the other software replace Logger Pro if a student cannot run Logger Pro? So if for most of our sensors, the graphical analysis software works fine on any platform. So if you're talking about temp probes or pH probes, that sort of thing. Graphical analysis works great, and it runs on computers, Chromebooks. If you have wireless sensors, it also runs on phones and tablets. So Logger Pro is only computer software. So that's something that we get a number of questions about. So there's a question about Spectra. I'm wondering, Melissa was asking about, can you overlay the two spectra on one another? So in graphical analysis, you can have more than one graph displayed on the same graph, just simply by tapping on the y-axis label and turning on whichever run you want to display at the same time. So you can have more than one on one graph. You can also split them into separate graphs if that's something that you want to do.
Yeah, so I showed it on Labquest here by selecting all runs. To change what you see in graphical analysis or in instrumental analysis, you click on the y-axis label here, and then you turn runs on and off that way. And also we went quickly over it, but I can name them here. And then as I overlay them, you can turn on the graph legend. And so it makes it a little bit easier for students to see all that. So there's the legend is down here, turn on graph legend. And now I see which one's water and which one's sucrose. Yeah. Great. What other questions have come up or have people had?
Nothing new since the last one that we talked about with Logger Pro. But one thing that I do want to point out is what Melissa just did is a workaround using a Labquest in order to get the older chemical polarimeter data into newer software. And so you do what she did does require a Labquest 2 or a Labquest 3. But if that is a concern and you happen to own that hardware already, it is a way to get that data from into a newer piece of software, which in this case would be graphical analysis. So so that's a thought. We do have some schools that they have a lot of our equipment, but they want to move forward, and how can they integrate what they already have with what they want to buy? And so this is what Melissa did, was demonstrate that. So we're getting close on time. Are there any last minute questions, concerns that anyone would like to pose? I'm not 100% sure. I think you can unmute yourself if you want to talk, but we'd be happy to hear your voice, or just throw it in the chat. Melissa, do you have the links on your thing where they can contact us?
Oh yeah, so yeah, if you have other questions, again, our website has a bunch of great information. Chemistry specific questions can go to chemistry@vernier.com. That's me, Noose, and our third chemist who's not here today, Elaine. We check that email, and if it's not chemistry related, we'll get it to the right person. There's also chat on our website. So feel free to open a chat window and talk to us, and you can call us. I always forget about calling because.
Oh, what? Call
Yeah.
and talk to a person?
No.
Oh my gosh.
Yeah, fill out a form online.
It's one of our favorite things. Sometimes people will apologize. Hey, I hate to waste your time. You're not wasting our time. We love talking to you. So
yeah, and that's how we get all our great ideas. I get lots of experiment ideas. I get lots of product ideas from talking to customers. So the polarimeter is one that came from customers. So and
if
all
you
the changes.
If you happen to be in West Lafayette, Indiana, in a couple of months, we are going to be at BCCE, and we're running 4 workshops, and 1 food, 1 forensics, 1 electrochem, and gosh, what was the 4th one, boss? Kinetics. Kinetics. We're going to do kinetics. She demonstrated kinetics with polarimetry. We're going to do kinetics with the pressure sensor, just to be a little different. Elephant toothpaste reaction. So if you happen to be near Purdue this summer, we would love to see you.
Yeah, and we'll also be at the Fall ACS conference.
Yep.
In the exhibit hall. So if you have any questions, you want to see the equipment in person, definitely stop by. Thank
Okay.
you all for being here.